Okay, welcome back for the second part of the celebration today. You cannot hear me. Now you can hear me. Excellent, wonderful. Now it's even louder. I should not. Okay. If everybody's quiet, then you can also hear me more easily. So we'll proceed now with the second part, in which we will first have the Laudatio of Helmut Friedrich, and then we will give the medal to Piotr Chruściel. I would like to now welcome also the Dean of Mathematics, Radu Boc, where is he? And also the Vice Dean of Physics, who represents the Faculty of Physics, Roberto Cervino. It's great to have you here as well. So now let me briefly introduce Helmut Friedrich, who will give the Laudatio for Piotr Chruściel. Helmut Friedrich got his PhD in Hamburg. Then he went to various places, working with Stephen Hawking in Cambridge, returning to Hamburg, and then doing research stays in various places, including Pittsburgh and the Courant Institute. Returning to Europe, he went to the Max Planck Institute in Garching, and then later he joined the Albert Einstein Institute in Potsdam, and we're going to hear from him about the life and work of Piotr Chruściel. Please.
Not so much about the life,
Not about
but I hope a bit about the work. I met Piotr Chruściel some time ago in 1988 for the first time at a relativity workshop in Canberra in Australia. At that time we were working on quite different subject, and for me he was just one of those guys doing elliptic things. In the following years, when I met him more often, I realized that he is a serious scientist and does challenging and scientifically important problems. So it gives me a great pleasure that Piotr Chruściel is awarded now the ASI medal in recognition of his many scientific contributions. And I feel honored to be given the opportunity to say a few words at this particular occasion. Piotr is unusually productive and versatile, with many scientific interests. He studied various important mathematical problems, but his main interest is devoted to the exploration of Einstein's theory, in particular to the exploration of Einstein's equation. There it is. We have seen that before, but I wanted to have an extra line for this. Now, if you look at this, it's just one line. It looks very simple. Trying to understand what it means is a little bit like trying to unravel some poems. You keep staring at them, and the longer you do this, the more thoughts are created. Now, I do a little bit history. Many bright minds devoted their time to unlock the secrets of this equation. My spectacle is not good. Some early researchers managed to find simple solution of these equations, but then it turned out that most of the solutions they found showed bewildering features and were absurdly inconsistent with the idea people started with. In the case of Friedmann's solution, it took 42 years and unexpected astrophysical observations before the wider scientific community was prepared to accept its consequences, and we have seen today this is still going on. In the case of Schwarzschild's solution, it took 23 years before a possible role was disclosed about of the event horizon, as it was called later. And it required more theoretical research and the development of new astrophysical tools until the idea of black holes began to take roots. In the 1960s, still many astrophysicists were skeptical about them. Anyway, these developments changed our conception of the world in ways Einstein could not have anticipated. We had to accept the solutions are so much wiser than the scientists who solved them. Einstein's equation and the apparent quirks of solutions had to be taken seriously and carefully investigated. The repertoire of phenomena offered by the equations, even in restricted section of the general theory, can be seen, for example, in Piotr Chruściel's masterly written book, Geometry of Black Holes. For many years, Piotr was the leading authority in the classification of stationary black holes. Recently, he managed to complete the theory, and I think it's a major achievement. Even when he explained deep ideas, Einstein used an unpretentious, in fact, deceptively simple language. During the 100 years during which these ideas are being studied, this language had to make room for notions, mathematical terms, abstract concepts, and technical representations nobody had thought of before. To show that the explicit solution mentioned before are not just exotic outliers, a general and detailed analysis of the equation, its manifold of solutions, and the particular properties of specific solution is needed. For this, the equation must be taken into its part and analyzed by abstract methods. The initial data, that is the field configuration at some cosmic time which we choose to understand as now, is subject to constraint equations by which the Einstein equation restricts the initial data. These constraint equations are nonlinear and underdetermined elliptic, so leaving some freedom to prescribe data. The evolution equations inherent in the Einstein equation control how the field configuration now changes as time goes by. They are also nonlinear. The evolution equations and the initial data decide whether the resulting solution space-time will admit non-isometric maximal extension, develop singularities, or any other strange features. We have seen how strange singularities can be. I'm not going to explain this notion here. We had some explanation already, but I assure you that even the scientists needed quite some time to develop these notions and to understand their significance. Today, even school kids hear about Big Bang, black holes, and the accelerated expansion of the universe. However, the scientific writing and the question being asked today in the mathematical analysis of these things become increasingly more technical and require more and more refined methods. This is the scientific realm Piotr is moving in. In his numerous research papers, monographs, overview articles, and books, he extended the range of this realm and our understanding of it into various important directions. I would like to outline two examples, knowing quite well that in doing so, it's impossible to avoid technical details, and I have to throw under the carpet thousand complicated subtleties and details which the connoisseur likes so much, like Piotr. Right in the beginning, when he developed general relativity, Einstein discussed in his new theory the concept of mass or equivalent energy, which is important in all parts of physics. Piotr was already early in his career intrigued by the peculiar form this notion of mass takes in this theory, and he took a long-lasting interest in it, trying to clarify the arguments leading to it and the precise conditions under which it makes sense. To simplify, assume that the energy momentum tensor T is 0. I assume that the cosmological constant lambda vanishes as well. And I also assume that the space-like set on which our data will prescribe, the set we called now, is similar to a set of fixed time in Minkowski space, in the Minkowski space-time of special relativity. This does not mean that the solution is Minkowski space-time. There can still be gravitational radiation around. Since radiation will disperse, however, we can assume that our solution space-time approaches a Minkowski space-time for large distances and late times. Such a solution is called asymptotically flat. The initial data on the set now consists of a 3 metric. That's a field which is designed to measure distances on this initial slice now, and another field which is not so important here for us. Together, they satisfy the constraint equation, and the metric approaches at large distances at infinity the Euclidean metric. The mass associated with this asymptotically flat space-like initial data set can now be determined. What one does, one uses the metric and its derivative to define a certain function. Then one performs a certain integral over a sphere, an integral of this function over the sphere. And then the mass is defined as a limit as this integral when the radius of the sphere goes to infinity. Schoen and Yao proved the highly non-trivial fact that the mass so defined is negative and vanishes if and only if the space-time involving from the data is Minkowski space-time. This is, of course, what one wanted to have from this notion of energy or mass. And I think it's remarkable that this one number called mass here gives so much information on the solution. If it's vanished, there was never radiation in the past, and there will never be radiation in the future. We want the mass to represent, however, the total mass of the asymptotically flat vacuum spacetime. Now, if you take our initial data and let the spacetime evolve, there are many other possible initial data which can be filled in. And what we want to have is that the mass associated with those initial data set is the same as the one we started with, so that we can say the mass is really related to the evolved spacetime. And Piotr stated precise condition on the asymptotic behavior of the metric, which should ensure this to be true. He announced the result as invariant mass conjecture for asymptotically flat spacetimes. It withstood the test of time and is a major contribution to the theory. In the case of flat asymptotically vacuum solutions just mentioned, there still exists another notion of mass. For simplicity, consider a light bulb. If at some space-time point it is switched on and switched off immediately, then a sphere of light will spread from this point in all directions. And in the end, it will go to infinity. The space-time set traced out by these two-dimensional spheres of space-time points extend to infinity. It's called a null hypersurface. If the light bulb is kept burning instead, however, then the light keeps coming out of it, and the whole set of space-time points lying in the future of P, of the point P, which I will call shortly the future of P, will eventually be illuminated, and our null hypersurface will be just the boundary of this set. So we have the future of P, and we have the boundary of the set, which is the null hypersurface. We can now calculate the Bondi mass associated with the future of P. One performs a certain integral over the light sphere and takes its limit as time, and thus also the light sphere goes to infinity. Again, this quantity has remarkable properties. The first one is similar to the one we heard about already. This mass, the Bondi-Trautmann mass, is never negative. The second property is somewhat different. If the Bondi-Trautmann mass of the future of P is 0, then the solution is Minkowski in the future of that point, saying that there is no gravitational radiation left. There is a big difference. In the first case, we had this mass which was defined at space-like infinity, and we said if that vanishes, there never was radiation and there never will be radiation. In this case, the mass is defined by limit in null direction, and we find if that mass vanishes, there's no direction in the future of P. And there's a third interesting relationship. If the mass is positive, then there's still gravitational radiation around. And if the point P is shifted towards the future, so that its future decreases, then its Bondi mass decreases by its design as well, indicating that radiation is leaving the system. So the Bondi mass is a very interesting object related to gravitational radiation. I can still ask, why should this notion of mass be so interesting? For that, I changed the picture slightly. Imagine there are, in fact, two black holes that approach each other and then merge to form a new black hole. In this process, huge amounts of gravitational radiation will set free and propagate into a close neighborhood of the point P. The effect of this propagation is that it deforms our space-time, our null hypersurface starting at P, and also the Bondi-Trautmann mass related to this. Since null hypersurface will eventually pass distant observers, for example, observers like us, its Bondi-Trautmann mass will provide them with astrophysical information about the black holes in the merger process. And of course, that's what we want to have when we want to develop some gravitational wave astronomy. I should say at this point that, of course, you get the control, that means relation of the incoming black holes and the outgoing radiation, only if you have control over the whole set given by the future of P. And Piotr studied these sets by studying the data which one may prescribe on this null hypersurface and the solution which is determined by them. So insofar his research is related very much to gravitational radiation. Of course, I simplified things, I told you already. Working out the details requires an enormous effort, and moreover, there are other situations which ask for similar analysis. For example, in cosmological asymptotically de Sitter spacetimes with a positive cosmological constant, there are space-like and null hypersurfaces that approach future null infinity. In asymptotically anti-de Sitter solution with a negative cosmological, there are space-like and future hypersurface, not future and null hypersurface that approach space-like infinity. Piotr considered all these cases under various assumptions, defined suitable notions of mass, and discussed many consequences. These things are just too technical to be discussed here, but summarizing, we can say Piotr is the leading expert concerning the notion of mass and the role of mass in general relativity. The second example I want to outline is of quite a different nature. In the 1960s and 1970s, there was developed the so-called conformal method, which became the main tool to construct solutions to the constraints. It is, however, somewhat clumsy if it comes to modeling specific physical situations. And here the method of gluing of initial data, which was developed more recently, represents a significant step forward. In the simplest case, it asks the following question. Imagine you are giving two subsets of asymptotically simple solutions. Can there be found a third asymptotically flat solution into which these two subsets can be embedded isometrically, or just in non-technical words, which contain these two subsets? Corvino and Schön developed a gluing process that exploits the underdeterminedness of the constraint equation in a completely new way. They constructed asymptotically flat vacuum data which coincide in the interior with a prescribed interior of some asymptotically vacuum data set, and near space-like infinity with an exact Schwarzschild solution whose mass is determined by the gluing procedure. This is remarkable, so we have something which we can choose in the interior, and then we can glue it to an end which is exactly Schwarzschild. At the time when the conformal method was only available, this came as a surprise. These asymptotically flat initial data, they could not have been found only on the basis of the conformal method. I happened to meet Corvino and Schön when they were still engrossed in finalizing the technicalities of their result. Of course, they knew they were after something remarkable, but talking to them, I realized they had not had the time yet to spend much thought on the nice things that could be done with the technique. After the work had been published, I was more surprised to see how fast Piotr, in joint work with Erwin, presented a new analysis of the structure of the constraint equation, worked out important generalization of the work of Corvino and Schön, and managed to control the method to an extent which allowed them to combine it with some known results about the time evolution to answer a long-standing question. They showed the existence of a large class of asymptotically flat radiative vacuum solution with smooth asymptotic structure in the future and the past. This result is rather complete and very easy to state. But I think it should not be taken for granted. And there I think it's worth recalling that well-known experts, well-known for their work on the global control on asymptotically flat Minkowski solutions, on asymptotically Minkowskian solutions, had called in print the idea that such solution might exist as questionable. In the following years, further types of gluing techniques were developed. Piotr was inspired by this method and made extensive use of them, sometimes widening the possible range of their applicability. And he wrote a series of articles that brought a rich harvest, which I just can't list here. All of these results were important and deserve seminars by themselves. For the most important outcome of his work, for me, the most important outcome of the work of Piotr is a demonstration of the enormous new freedom gained in the construction of initial data with prescribed properties. It will allow us to study models of the world which were not accessible before. After having seen that the scientific realm of Piotr's research covers the most remote corners of cosmologies, fields of stars, black holes, interacting system of these, and also the gravitational waves filling the space-time in between, it is interesting to note that also the interaction of technical devices with gravitational radiation, in particular the response of laser interferometers on our Earth to the gravitational waves that impinge on them, arouses his interest. To appreciate this more recent interest, it should be observed that a large part of the theoretical background of the exciting gravitational wave astronomy ahead of us relies on mathematical approximations. When this type of astronomy will develop maturity, it can be expected to ask for new standards concerning the reliability and the precision of the theoretical background. It is precisely this kind of problem that Piotr addressed with Thomas Mieling and Stefan Palenta in their paper, The Electromagnetic Field in Gravitational Wave Interferometers. I think already that fraction of the work I was able to indicate here should make it clear that Piotr's scientific contribution pushed the boundary of our knowledge far into previously uncharted domains. So I could stop here, but coming to the end, I feel a desire to mention at this occasion a fact that is usually neglected when one speaks of scientific contribution. On the one hand, there seems to be nobody else I know who, besides writing articles, research monographs, and books by himself, published so many pieces of work jointly with so many different collaborators, sometimes over many years. On the other hand, he expertly organized various summer schools, conferences, and extended high-standard workshops to attract young people to the field. I consider this as an important service to the community and thus to our science as well. Thank you very much.